Right.
So very good morning, sir.
Good morning,
Good
people.
morning, sir.
Good morning. Something is different. Oh, I have not put a webcam here. We are using laptop camera right now, and hence the angle is wide. But I think people is the clarity fine with the laptop camera on as well.
Yes, sir.
That's fine, right? Okay, okay. So we'll continue with this then. Okay. So, hang on. Wait. We have started with our chapter on postulates of quantum mechanics, and I just introduced you all to this chapter in the last class, and we had learned a couple of things in this. Right. We had learned the first postulate that was related to well-behaved wave function, and I told you that a well-behaved wave function has three most important properties. First of all, it should be single-valued. Second, it should be finite. I tried to explain you the meaning of finite. Basically, it can never become infinite. That's what we call the set. If it is becoming infinite, I'll not remove the constant. Say that the constant is zero. It means the term doesn't exist at all. Basically. Okay. So whatever was the constant, if you have, like I said, sine is a e raised to x. Okay. So it becomes infinity at sine becomes infinity if x is infinity, because e raised to infinity is infinity. So it should not exist. It means allot the value zero to the constant so that the wave function is eliminated. So it should always be finite, and then we learned that it should also be continuous at the boundaries. Continuous, not only the wave function but also its derivatives. That way we can have two equations also in order to solve any problem. Function and its derivatives should be continuous at boundaries. Okay. So now let's learn from the next postulate. Second postulate. Let's get started. Second, I have already introduced you to, and that is observables and operators. So this you already know. Observable and operators. So observables are nothing but physical quantities. Okay, any physical quantity that is studying quantum mechanics. That's fine. Okay. So energy, momentum, position, all of them are observables, and every observable has its own individual operator. So to any observable, you can say to any observable. If I just say to an observable, there exists a respective operator. And we learned the three important operators. Like for example, a position operator is position itself. We learned that the energy operator is minus x square upon 2m plus dou square upon dou x square. Okay, and then we learned minus x square upon 2m dou square upon dou x square plus v of x. Like this is basically V's potential energy. So that was our that's what we call it. Energy operator, also known as Hamiltonian operator. You can also write E cap, doesn't matter. So E cap is energy operator. Hamiltonian operator was this. This we derived using kinetic energy plus potential energy. Kinetic was p square upon 2m. Okay, and after energy operator, we had learned momentum operator too. That was minus I h square dou by 2x. Okay. So position has an operator, energy has an operator, momentum has an operator. These three are the most important operators. Rest are fine. Do ask me if you have any questions. Done, people? Next. Then third, measurement. Okay, so postulate related to measurement. So all we have to do is we apply. I've also taught you this before. So we apply an operator. Whose observable we want to calculate. Whose observable we want to calculate. Like if you want to calculate energy, we'll apply energy operator. Simple. Whose observable we want to calculate. Keep this in bracket. So we apply an operator on the wave function. Okay, so we'll have something like this, an operator applied on the wave function, and we'll have energy eigenvalue and the same wave function. This is our eigen equation. So this is how we can measure anything. Eigen equation. So this is our measurement value. This is measurement. Simple. So if I want to calculate energy, I'll apply energy operator, I'll get energy value. If I want to calculate momentum, I'll apply momentum operator, I'll get momentum value. So this is our measurement. So eigen operator, eigen function, eigen value. That we also know. This is your eigen operator. This is your eigen function, and this is your eigen value. We can have multiple eigenvalues like you know. So if you apply energy operator on a function, you can get multiple energies also. That's fine. So you can have multiple eigenvalues. And to every eigenvalue, what happens? There exists an eigenvector, like you know. To every eigenvalue, there exists an eigenvector. And there was a request in the last class, I remember, that if I could take an example where I can teach you how to calculate eigenvalues and eigenvectors, main eigenvectors basically. So we'll take that now. Every eigenvalue that exists an eigenvector, such that, you know, such that the eigenfunction that we have is linear combination of all the eigenvalues. You can write like C1 phi 1 plus C2 phi 2 plus Cn phi n. So this is the eigenfunction. And that function is basically linear combination of eigenvectors. Okay, so phi 1 is basically eigenvector of corresponding to eigenvalue lambda 1 so A1. This is eigenvector corresponding to eigenvalue A1. Okay. All this we have learned this before in the previous chapter. Directly, I remember telling about these, but still we are going through this first. So eigenvector corresponding to eigenvalue A1. And similarly, phi 2 is eigenvector corresponding to eigenvalue, you can say A2, whatever, anything you want. C1, C2, Cn are constants. That's right. C1, C2, Cn are just random constants. Do ask me if you have any question, people. I'm not putting much effort and strain while explaining these things because we have done these things, but they are very smooth as well to understand. So I'm not putting any stress here.
Yes, sir.
Okay. So let's take a random example, okay, on where we can learn how to calculate eigenvectors maybe. Well, I'll just create a random matrix. Suppose we have been given minus 6, 3, 4, 5. Okay, and this is it. Okay, no problem. I will take this. Hang on. I will take an identical question only so that we can have a reference after getting the answer. No problem. So, okay, minus 6, 3, 4, 5. Let's calculate eigenvalue first of all of this. So, how do we start? This is a matrix, number 8. So, I want to start with the first of all eigenvalues exist or not. Now, in order to find whether they exist or not, first you do is you calculate the determinant. So, let's calculate the determinant. Minus 3, 6, 3, 4, 5. So, this is minus 30, minus 12. So, that's minus 42. So, people, this is not equal to 0. This is a non-singular matrix. And eigenvalue can exist. This is a non-singular matrix. There is a background noise. So, this is a non-singular matrix. Okay, eigenvalue can exist. Eigenvalue exists. Okay. So, now we want to find eigenvalue, people. The first thing now we do is we calculate a minus lambda into I, where lambda are eigenvalues. How many values will we have? 2, because it's a 2 cross 2 matrix. It's a 2 cross 2 matrix, so I will have 2 eigenvalues. If you have a 3 cross 3 matrix, you can have 3 eigenvalues. So now we'll have 2 eigenvalues. So let's calculate a minus lambda I, where lambda are eigenvalues. So lambda will be there will be 2 lambdas, lambda 1 and lambda 2, you can say. Sorry. So there will be 2 lambdas, lambda 1 and lambda 2. Okay. So lambda just I'm writing in general right now. Lambda is an eigenvalue right now. Okay. And I is an identity matrix. Identity matrix. Okay. So let's calculate a minus lambda I. So this is a is minus 6, 3, 4, 5 minus of lambda into I, which is 1, 0, 0, 1. Okay. So this is minus 6, 3, 4, 5. This is minus of lambda 0, 0, lambda. Lambda will go inside, so it multiplies to all of them. And now subtract all the respective terms, people. So minus 6 minus lambda, and then 3 minus 0, and then 4 minus 0, and then 0 minus lambda. Okay. So we have calculated a minus lambda I. Copy. Okay, you can tell me to write it. So we have minus 6 minus lambda, 3, and then 4, and then minus lambda. So this is our a minus lambda I equation. This is known as characteristic function also. Characteristic function.
Minus lambda, so this 5 minus lambda.
Okay, I've written 5 minus lambda. Oh, yes, absolutely. Here it's 5. Absolutely. Thank you. 5 minus lambda. Yes. So this is a characteristic function equal a minus lambda I. Okay. And basically, we can also call this eigenfunction. We say that this is eigenfunction. So this should obey eigenequation then. Okay. So what is eigenequation? When you operate the eigenfunction on a matrix, we should be able to. Sorry. This is different. A minus lambda I we have calculated. A is actually better. So I will just say. Just nothing. So just calculate now determinant of this a minus lambda, and we equate this with 0. This is known as secular equation or characteristic equation. And you can call this also characteristic equation. Probably secular is the word that is secular equation, right? So let's calculate the determinant of this. Minus 6 minus lambda, then 3, 4 minus lambda. This is 0. So we have minus 6 minus lambda into minus lambda minus 12. This is 0. Open the brackets.
5 minus lambda.
Sir, 5 minus lambda.
Right. Yes. So we have minus 6 into 5. Minus 6 and 5, that's minus 30. Minus 6 into minus lambda, that's plus 6 lambda. Minus 5 into lambda, that's minus 5 lambda. And then minus lambda into minus lambda, that's lambda squared. Minus 12, that's 0. 6 lambda minus 5 lambda is lambda. Lambda square I'm writing as it is. Minus 30 minus 12, that's minus 42. This is 0. So we have an equation. Now this is also known as, this is the same thing, secular equation only, but you have written this in terms of lambda. Okay. And yes, this is also known as characteristic equation. By the way, by any chance, it's not actually exclusively present in JAM syllabus, but have you ever learned something called Cayley-Hamilton theorem?
Yes, sir.
You know?
Yes, sir.
Yes, sir. इन्वर्स निकालने के लिए यूज होते हैं.
Okay.
हर मैट्रिक्स अपने अपना characteristic equation को satisfy करता है.
Exactly. That's it. That is what I want to. So the point is, this equation is also now valid for the same matrix also. So you can always say that this can be written as a square plus a minus 42. If you will calculate this, your answer will be 0. So characteristic equation is satisfied by its own matrix. So whatever is the eigenvalue, whatever eigenvalue you found out using a matrix, that same equation now is valid for the whole matrix also. ठीक है. तो आपका जो ये matrix है, इस LHS you can calculate people. Calculate a square, calculate a, calculate 42, minus 42, subtract all of them. This is basically 42 when you write 42i. A square is a into a, but then you can calculate. Okay. A you already know, and minus 42 means minus 42 into I. Identity. Calculate this and you will get 0 people. So this is the Cayley-Hamilton theorem. But anyway, so now let's find eigenvalues people. Lambda square plus lambda minus 42. This is 0. So I have lambda square. This is factorizable. 7 lambda minus 6 lambda. 7 minus 6 is 1. 7 into minus 6 is minus 42. So very much factorizable. If it is not factorizable, then you can use the formula minus b plus or minus under root b square minus 4ac upon 2a back. That's also fine. Lambda common, lambda plus 7 minus 6 common. Lambda plus 7, this is 0. So I've taken lambda plus 7 common and I've got lambda minus 6, this is 0. So we have got basically lambda plus 7. Either this first bracket is 0 or the second bracket is 0. Somebody must be 0 because the product is 0. So lambda is minus 7. And lambda is 6. Either of them is correct or both is correct. We don't know. But we'll say, let's say both is correct. Lambda is minus 7 and lambda is 6. These are our two eigenvalues as expected. People, we wanted to find two eigenvalues. Lambda 1 is minus 7, lambda 2 is 6. This you already are well aware of. I just took you through maybe a larger process, try to give you a bit more insight. Now, just after you get the result, also ensure that it's correct. So again, you must have learned what is product of eigenvalues. It is equal to
Determinant of the
Determinant.
So after getting value, just check whether you're getting determinant or not. So minus 7 into 6 minus 42 was our determinant minus 42? Absolutely. So once you get the eigenvalues, just verify for a second so that you don't mark the wrong option. Because what if you have done some calculation error? Like for example, if you wouldn't have told me that this is 5, if I would have done something else, then my answer wouldn't have matched up. I would have went back and checked that something has definitely went wrong. So always after getting the values of eigenvalues, just multiply them and see if it is equal to the determinant or not. Okay. And also, what is the addition of eigenvalues, people?
trace of the matrix.
Trace of the matrix.
Also check that also. Minus 7 plus 6 is minus 1. So is the trace minus 1 or not? That you can check. Minus 6 plus 5, absolutely trace, which is also minus 1. So addition of diagonal elements, that is nothing but a trace of addition of diagonal elements. Okay. So after adding the value, you can always check whether sum is giving you trace or not and product is giving you determinant of not. Just to be confident about what if your result is correct or not. So that's eigenvalues. Now let's calculate eigenvectors corresponding to each eigenvalue. Done, people? Let me try again. Anything? Okay. So we want to find eigenvector corresponding to minus 7. Suppose lambda equals to minus 7. Understand that eigenvector is also a function, people. Just that it's linearly independent function. Because I told you now that your wave function, you can write the wave function as linear combination of the eigenvectors. So eigenvectors are also nothing but functions, people. But they're linearly independent functions. They don't depend. Like 5 and 5 are independent of each other. The wave function can depend on both of them, however. 5 and 5 where they are eigenfunctions. So the point is, when you say eigenvector, it is an eigenfunction in itself, people. So eigenvector also obeys eigenvalue equation. Eigenvector, they also obey eigenequation. Because they are also functions only. Okay, so what is eigenequation? Like, a into x is lambda into x. So here you can say, let's say this eigenvector is x1 then. Okay, so I will say whatever was the matrix into, let's say right now this eigenvector is x1 corresponding to eigenvalue lambda. Similarly, you can also say that a into x2, this is lambda 2 into x2. Okay, x1 is the eigenvector corresponding to lambda 1, x2 is the eigenvector corresponding to lambda 2. This is x1 right now. They will also be eigenequation because they are eigenvectors which are nothing but a function in itself, just linearly independent functions, you can say. Okay, let's calculate this. So let's start with a into x1. This is lambda into x1. So a, what do we have, people? A is minus 6, 3, 4, and 5. Okay, and x1. So we don't know the value of x1. So we will say, let's say it is x1 or x2. You can also write x and y. You can write anything. Okay, this is lambda. What is lambda? Lambda 1 into x1. So lambda 1 is minus 7 into x1. I'm again saying, let's say x1 is x1 and x2. We have just said now, let this eigenvector that we have, let's say it's a column vector x1, x2. So now let's calculate. If you're thinking, what's the y column vector? Well, it's simple. RHS, suppose if it's 2 cross 1, if this is 2 cross 1 and if this is 2 cross 2, is your answer matching or not RHS RHS? They are not, because 2 into 2, they can be multiplied and your resultant should be 2 cross 1, which you're getting also. So it should be a column vector. Okay, so that RHS and RHS needs to be. Because you cannot have a row vector, because otherwise they are not multipliable. This is when this is 1, you cannot multiply them. In order to multiply any two matrix, the number of columns of the first should be equal to the number of rows of the second people. They should be equal. Here they become unequal. Okay, here you have 2 cross 2 and here you have 2 cross 1, here you have 2 cross 1. So these two are multipliable. Number of columns of the second is equal to number of rows of the first. So number of columns of the first is equal to number of rows of the second. Okay. Anyway, so now let's calculate. So let's multiply. So minus 6 into x1, that's minus 6x1, plus 3 into x2, so that's plus 3x2. Again, 4 into x1 is 4x1, plus 5 into x2, that's 5x2. We got 2 cross 1. This is take minus 7 inside. So minus 7x1 minus 7x2. We got 2 cross 1 on RHS also. Okay. So let's equate the terms, respective terms. So the first one is giving us. Why is the thickness reduced? Not sure. Okay. So we have minus 6x1 plus 3x2. This is equal to minus 7x1. Okay. This angle. Now it's fine. So we have about minus 6x1 plus 3x2. This is minus 7x1. Okay. So we have about 3x2 is minus 7x1 plus 6x1. So we have about 3x2 is minus x1 people. That's it. Or you can say x1 is minus 3x2. This is one of the equations that we have got. You will mostly have same equation people in second equation also. If you have suppose 3 equations, then you will have either all the 3 equations will be equal or at least 2 equations will be equal. The point is, you will never be able to find an exclusive value of x1 and x2. I repeat, you will never be able to find an exclusive value of x1 and x2. They will be generalized value. They will have a relationship. Even though you will have 2 equations, you will still be never be able to find 2 exclusive value of x1 and x2. If you have 3 equations, you won't be able to find 3 exclusive values of x1 and x2. You will get a general equation. Remember that. We won't get exclusive values. Unique values. Okay. Exclusive or basically you can say unique values. You can always check that. And I just want to ask, if I have got suppose like x1 is minus x1, if you get something like this, what is the meaning of this? What is the value of x1?
0.
0. Okay. Because only 0 is the term where 0 and minus 0 are equal. 2 and minus 4 are definitely not equal. Okay. 4 and minus 4 are not equal. But if x1 is minus x1, it only means that it's 0. Okay. So now let's calculate the second equation. So what do we have? 4x1 plus 5x2 is minus 7x2. So we have got 4x1 is minus 7x2 minus 5x2. So we have got 4x1 is minus 12x2. So we have got that x1 is 12 upon 4, that's 3. Like I said, people, did we get an exclusive value? No, we got the same equation. That will always happen. Okay. Same equation again. What is the meaning of this, sir? It means that there are infinitely many values possible. Many eigenvectors. Because what is our eigenvector? Our eigenvector, capital X1 that you have said it is small x1, small x2. You defined it this way. We started here, as you can see later. Okay. But the thing is, x1 and x2 don't have any exclusive value. They can take any values which obeys this relationship. x1 and x2 can take any value, any values. You can say value or values, whatever. Okay. That obey this relationship. That obeys this relationship. Okay. That's it. So you can say if x1, x2 is let's say n. If x2 is suppose n, or let's call it c1. If x2 is c1, a random constant, then what will be x1 be? Okay. Or don't call it c1. Let's just call it n. Okay. Or n1. If x2 is n1, then x1, which is minus of 3x2 now, so x1 will be minus of 3 into n1. So it will be minus of 3 into n1. Or you can call it c1 also. I'm thinking c1 and this, c1 plus this, c2 plus this. It will be linear combination of them. Absolutely. Okay. But okay, no problem. I will go with c1 now. Just a minute. I'm thinking which notation is. Suppose this is a constant c1. If you give a constant value c1, then x1 which is minus 3x2, so x1 will be minus 3 into c1. Okay. Copy. So any equation, any combination which obeys these two equations, they will be a part of the eigenvector capital X2. Okay, substitute. So our first eigenvector capital X1 is small x1 and small x2. This is what is small x1 people? It is minus 3c1. And what is small x2? It is c1. You can take c1 common people, minus 3 and 1. This is your first eigenvector. First eigenvector. C1 is just a constant. C1 is just a constant. So actually eigenvector could be any vector. You can say which can be multiplied with any constant. I mean, it is this vector, this eigenvector, multiplied with any constant. You can multiply with 1, multiply with 2, multiply with 5. All of them are nothing but first eigenvectors. But we started only the fundamental, minus 3 and 1. You can say fundamental eigenvector corresponding to first eigenvector, whatever. Minus 3 and 1. Okay. Similarly, you can calculate eigenvector corresponding to the second eigenvalue. And I think now you should be able to do this quickly. Eigenvector corresponding to second eigenvalue we can calculate. So the second eigenvalue is lambda equals to 6. Lambda equals to 6. So let's say this is lambda 2, and let's say now the eigenvector is x2. You can say let's say x2 is y1 by 2. just give it different letters. Suppose x2 is y1 by 2 later. Okay, so let's get started. Again, even x2 will be eigen equation people. So a into x2, it is lambda 2 into x2. Okay, so what was a? Minus 6, 3, 4, 5. Minus 6, 3, 4, 5. x2, which is y1 by 2. Okay, lambda 2, which is 6, x2, which is y1 by 2. Any questions, anyone, anywhere? Please ask.
Sir, y2 is equal to 4 by 1.
Okay, let's check quickly. So let's expand this. So what do we have? Let's multiply. Okay, so minus 6y1 plus 3y2, minus 6y1 plus 3y2, and then 4y1 and 5y2. 4y1 and 5y2. This will be equal to 6 into y1 and y2. So this is 6y1, 6y2. Equate, again, you will get only one general relationship this time. So we have minus 6y1 plus 3y2. This is 6y1, or I can say 3y2 is 12y1. Okay, so y2 is, as we said, 4y1. Good. Second should also give you the same equation. You can check 4y1 plus 5y2 is 6y2. So we have got 4y1 is 6y2 minus 5y2. That's y2 as expected. So y2 is 4y1. So again, you can say that let y1 be c2. So in that case, y2 will be 4 into c2. So your eigenvector, second eigenvector, which you said it's y1 and y2. So if y1 is c2, y2 will be 4c2. What will your eigenvector people? Can take c2 common. It's 1 and 4. Any such combination will always go depending upon the value of c. C is a random constant. It can be decimal also. We don't care. Any equation which satisfies like any value of constant c1 or c2 which satisfies this relationship. Where y2 is 4 y1. Like you can give y1 is 1, y2 becomes 4. You can give y1 is 2, y2 becomes 8. You can say y1 is 0.5, y2 will become 2. There are infinite combinations. You can give whatever value to y1. Anything which obeys this relationship, that's your second eigenvector. Okay. Or you can say this is a second fundamental eigenvector, or second eigenvector corresponding to second eigenvalue, whatever. There are exclusive terms for this. So 1 and 4 is the eigenvector. 1 and 4 is the eigenvector. 1, 4, as a column vector of 1, 4, corresponding to the second eigenvalue. Any questions, anyone? Yes. And like I said very early, the wave function, people have the wave function, it will be a unique linear combination of the individual eigenvectors. See if you are able to find a unique linear combination or not. Let's check. Okay. So what is the original wave function? Original wave function means the original operator, people. Capital this, what do you say? Actually, we don't have a wave function yet. They have not given us this. Capital X, sorry. Okay, but there's an operator in x1. Okay, so this will we can have in quantum. So basically we can define any wave function here. Okay, we can define any wave function. So that will be unique linear combination of x1 and x2. So x1 is basically cx1, c1 x1. Sorry, x1 you can say c1. What is c1 into this? Hang on. c1 into what was the first one? Minus c1 plus c2 into we have 1 4.
1 4.
Yes. Okay. So this is your basically you can see c1 into the first fundamental eigenvector, c2 into second fundamental eigenvector. So depending upon c1 and c2, whatever wave function they will give you, it will be a unique linear combination of it. Okay, this becomes a wave function. Okay. The original eigenfunction, whatever they give you, that will be a linear combination of the sets. So depending upon c1 and c2, you can define infinitely many wave functions here. These two are independent, but all the others will depend on them. All the others will depend on them. Okay. I hope the process is understood completely.
Yes, sir.
Good. Remember, you will never have exclusive values. That's important. Chalo, next. Now, here's a couple of more important things. So, people, we have learned the Max-Born interpretation that Px dx represents probability from x to x plus dx. We have learned this.
So this is the fourth postulate.
I think so, no? With different 3 so far.
Yes, sir.
So integration of Px dx, this becomes it will have some value. It will have some value. So this is your probability. You can say from A to B. This is probability between A and B. Between A and B. And then integration of this Px dx, we have learned, is equals to 1 over all space. All space does not necessarily mean minus infinity to infinity. They have to give us that what is the confinement area. So integration of probability in that confinement area that will be done. So this we have learned before. That's fine. Continuing that, the normalization condition, people, was the value of psi should be 1. Okay, so when you say that the value of psi was 1, you can also say value of mod psi square integration of dx. This is 1 over all space. Okay, so it also means integration of psi star psi dx. This is also 1 over all space. So this also we have learned. Okay, next. Then people average value. We are still continuing with the fourth postulate. Actually, I want to read somewhere, as in this postulate. So the average value of any observable. Suppose in exam they ask you what is the average value of energy, what is the average value of momentum, anything. Average value of any observable. I'm not written operator because this is observable. This is variable. Observable. Okay. It is given by integration of whatever is the limit they're asking you to find. Okay. So integration of psi star. You will apply the operator corresponding to this observable into psi dx upon integration of psi star psi dx. See, many books write only this much people. People, when can I write it? Only numerator. When can I write it?
When the function is normalized.
But that's it. Denominator should be 1 in that case. So if the book has written this, that's only possible that the denominator is 1. But this is a general formula. Okay. So if function is normalized, then denominator is 1. That's fine. If function is normalized, then denominator is 1. So in that case, our average value, it will be simply integration of psi star eta psi dx. That's fine because denominator becomes 1. Then denominator is 1. Okay?
So you can go to the previous slide.
Sure. So by the way, also remember, I've been writing dx everywhere. You can also write it dy if you are along y-axis, you can write dz if you are along z-axis. Then in 2D world, we can have area. In 3D, we can have volume. You can write dA, you can write dV. So this thing will completely depend if you are in 1D world, 2D world, or 3D world. dx, dA, or dV. We can have dx, we can have dA, we can have dV also.
Yes, sir.
So even later when we learn hydrogen atom once again, so there also I think there was a question where they asked to find the average value of the position or whatever, something like that for the ground state. So what students have done is, so whatever is the PR value that they give you, and by the way, this is PR, not psi square, this is basically PR technically. But hang on, I was saying, so whatever is the PR value that they are giving you, the function value, suppose, forget this. So students will calculate this and they will write a DR and they will get the answer. But that will give you a wrong answer. Because in hydrogen atom the word is 3. So here, unless they have mentioned clearly that you are in 1D box or whatever. So here you have to write dV. If you write dV, so will I have R square then? No. In dV, what should I have people?
You have spherical coordinates.
Yes,
Square.
yes.
R square dr sin theta d theta d phi.
I mean directly write the 4 pi R square here.
First,
But you said it's correct, but after integrating that you will get 4 pi any. If you calculate sin theta, d theta, d phi.
Yes, that's spherical symmetry.
So you don't get that. Okay. So in case of dV, you have to write this. So obviously, you get this with a very different result now, very different, because you have another R dependent stuff. But a common mistake which the student will do is they will end up writing dr. That's all. You have 4 pi R square here. For this secret that we are writing for multiple for 2 you have to read in the question what they are asking. Okay. Next. Now, so one thing like we already know that before measuring, we may have some value of wave function, which we don't know, which we will never know. We can predict that this is a wave function. Sorry, I'm saying that once we measure, we know we destroy the property of it, and the wave function will collapse into a particle. I hope you remember that by the experiment that I tried to do. Under the darkness, it was a wave, and it did not allow us to study it. But if we are going to measure people, then whatever wave function it has, it is collapsing itself into a single wave function which is attached to one particle. Because basically it becomes a particle. As soon as you open the lights, the wave collapses, it becomes a particle, and you can assign one wave function to that particular particle. Okay. So the point is how to find the collapse value of the wave function. So that's actually this postulate, fourth postulate all about. But I wanted to reach the fourth postulate basically. So let psi after is the wave function after the collapse. Okay. Is the wave function after the collapse. Sorry. After the measurement. You can call it collapse wave function also. Okay. After collapse. So how to calculate the psi after? Psi after people is calculated using k vector psi n into bra vector psi n into the value of psi t. Now what is psi t? I will tell you, don't worry. Okay. Upon mod of psi t psi t. Or no, mod of psi n psi t. Cannot be psi t psi t. Mod of psi n psi n. Okay. Okay. So psi t is the initial wave function. Psi t is the initial wave function. You can also write it psi I. Just psi I. If you don't want to write psi t, I mean, I've written, its notation is up to us. People don't write psi t. Let's write psi I. Let's test. Notation is completely up to us. Okay. Psi after is k vector psi n into bra vector psi n into k vector psi I upon mod psi n psi. Now this value again, denominator again becomes 1 if the function is normalized. Okay. So denominator can be 1 if function is normalized. That's fine. When we take numerical, you will understand how to calculate this. Don't worry. After taking the numerical, you will understand this. As of now, just copy.
Psi n is the initial wave function. Before
Psi I is the initial wave function. Okay.
Psi n.
Psi n is the total wave function that we will have. So for example, we will have psi n is C1 psi 1 plus C2 psi 2 whatever. And after this, what do you say? Wait, I'll take an example. Let me take an example. Right now, I'll try to do that. Let me find. I will take an example right now. By the way, so I was saying psi I is the initial wave function, which is linear combination of whatever, which they will give you C1 phi 1 plus C2 phi 2 whatever. What is psi n that you asked me? Okay, psi n. Okay, so suppose after measurement, we record it. We'll have one particle, will have a respective energy. We record it En eigenvalue or Xn eigenvalue. Like if it's energy En, then En. If it's something else, then something else. Whatever eigenvalue you are calculating. So suppose you have En eigenvalue, then psi n is the eigenvector corresponding to this eigenvalue. Psi n is the eigenvector corresponding to this eigenvalue. And I already told you that eigenvectors are nothing but the wave functions which we can use as like for the linear combination. So the initial wave function that you will have, suppose. So that will be, initial wave function. It will be linear combination of C1 psi 1, suppose C2 psi 2, and Cn psi n. Okay. And suppose what you do is you have turned on the lights to measure energy, and you found out energy. You found out that energy was, let's say, minus 3.5. Suppose in hydrogen atom, energy was minus 3.5. So that energy is for home people. We know that's for second level. That's for first excited state. Minus 13.6 is for ground state, and minus 3.5 that's for second excited state. Sorry, second level of first excited state. Whatever. For n equals to 2 basically. So the point is, you found out energy that was corresponding to n equals to 2. So all you have to understand that this psi n that you have, it is the eigenvector corresponding to energy equals to 2. It means it is psi 2 this time. No? Because eigenvector is what these are eigenvectors. Psi 1, psi 2, psi n. I told you that any wave function can be expressed as linear combination of the eigenvectors. So these are eigenvectors. So for like in case of hydrogen atom, you can write for hydrogen atom. Suppose after measurement we measure. Suppose we measure energy is minus 3.5 electron volts. It means it's second level. Simple. N is 2. Okay. So the eigenvector corresponding to n equals to 2, that will be psi 2. That will be psi 2. And how do we find psi after then? How do we find psi after? So psi after will be equal to, I can make you understand. It is psi n, which is psi 2, into psi I into psi 2, or psi 2 into psi, whatever we have. Psi n into psi I. So this will be psi 2 into psi I. Apply the formula. I'm applying the formula. What is the formula? The formula is psi n into psi I upon psi I. So this will be equal to, make it psi I, please. Make it psi I. initial wave function, no? Absolutely. Make it I immediately. Make the correction, people. Okay. So this will be psi 2 into what do you have? Psi 2 psi I upon psi I psi. Understood how to calculate steps. You have an initial wave function, understand? That is linear combination of all the eigenvectors. What is eigenvectors? It is the wave function of the particle corresponding to a particular energy level. So C1 psi 1, psi 1 is energy of E1, the wave function corresponding to E1. C2 psi 2, that's wave function corresponding to energy E2. Okay, so initial wave function psi I, which whatever wave has. So basically, white light, for example, white light is what we call a combination of wave iota. So very similarly, a wave function, it is combination of many individual wave functions. Psi 1, psi 2, psi 3, psi n. Okay, once you turn on the light, what will happen out of those psi 1, psi 2, psi 3, psi n? It will collapse itself to either of them. It will either collapse to psi 1, it will either collapse to psi 5, it will either collapse to psi 3, it will collapse to either of them. The question is, what is the wave function after the measurement? So wave function after the measurement, how do we calculate? It is first you write psi n. What is psi n? It is the wave function corresponding to the energy which you have measured. And then psi I is the initial wave function. That's it. Nothing else is remaining in that. Okay. So this is wave function after the measurement, or like a wave function corresponding to the energy you measured, initial wave function, and this is wave function after the measurement. I hope the formula is clear, people, without any hesitation now. Tell me if not. I can repeat. Psi after is the wave function after the measurement, psi I is the initial wave function, and psi n is the eigenvector corresponding to this eigenvalue which you measured after the measurement. Clear, people? Tell me. I'll take an example even in the sense better right now. I've always told you, don't take theory hard as far as you're understanding the examples and vehicles, that's important. Okay. Actually, why am I not able to see my own video? Hang on. Sorry. No, it's fine. Okay. So the question is, so they have given you the initial wave function psi t, which is given by 1 upon root 2 psi 1 plus 1 upon 2 psi 2 plus 1 upon 2 psi 3. So a wave function, like I said, a white light is combination of different lights, 7 lights for an example. So every light has different refractiveness, every different refractiveness will have its own wavelength, all of them will have own wave function, whatever. So likewise, this wave function is combination of 3 individual wave functions which are linearly independent on each other. All of them are nothing but eigenvectors. Okay? All of them are eigenvectors corresponding to the eigenvalue E1, E2, and En. I hope this is understood. All of them are eigenvectors corresponding to energy eigenvalues E1, E2, and En. You cannot get vectors by them. That's fine. Okay. And now suppose they tell us that. So first of all, we can always be a bit smart. Before solving anything in quantum, see whether this is normalized or not. No? Because what will happen if it is normalized? You don't have to play with the denominator. You can eradicate the denominator there and there. So let's calculate whether this is normalized or not. Just checking out. Checking normalization. Okay. So how do we check, people? The value of psi should be 1. So that's what we want to see. So the value of psi t into psi t should be 1. So basically the value of the bra vector of this product with the ket vector of this. Remember, people, eigenvectors always form orthonormal basis unless mentioned otherwise. Eigenvectors always form orthonormal basis. I told you the meaning of orthonormal. Do you remember? What is orthonormal? Yes, orthonormal plus normalized.
Stellar product G.
Dot product of, like when you write psi I psi j, this value will be equal to 1 if I is j, and this value will be 0 if I is not j. So psi 1 will be 1. Okay, psi 2 will be 1, psi 3 will be 1. But psi 1 psi 2 will be 0, psi 2 psi 3 will be 0, psi 3 psi 1 will be 0. If I and if this these two coefficients here, if they are equal, then it's 1. If not equal, then it's 0. So they always form orthonormal basis. So product of, basically it's like, you can imagine it this way. This is I cap, this is j cap, this is k cap. So you're taking dot products. I told you wave function is identical to dot products many times. Imagine this is I, this is j, this is k. So when you take dot product, what happens, people? I multiply with I, j with j, k with k. It means it's nothing but product of what? It's product of their own coefficients, individual coefficients. You can directly write 1 upon 2 square plus half square plus half square. You can directly jump on that. But let's, because we're doing this for the first time, let's calculate. So what do we have? The value of psi t is 1. That's what we set, normalization condition. So sorry, whether we want to see whether it's normalized or not actually. So we want to check that out. So this should be satisfied. So we're checking it. So the ket vector of this, people. So what is the ket vector of this? 1 upon root 2. I'll just directly write 1 upon root 2 psi 1 plus 1 upon 2 psi 2 plus 1 upon 2 psi 3 into bra vector of this, So this is 1 upon root 2 psi 1 plus 1 upon 2 psi 2 plus 1 upon 3, so 1 upon 2 psi 3. I've just written them as it is, not working on the notations continuous. So this is, all of these are bra vectors, people, all of these are ket vectors. I just multiplied the bra vector. But like we know, when you open the brackets, what will happen? Psi 1 and psi 1 will become 1, but psi 1 psi 2 will become 0. Psi 1 psi 3 will become 0 because they form orthonormal pieces. Similarly, psi 2 psi 1 will become 0, psi 2 psi 2 will be 1, psi 2 psi 3 will become 0, psi 3 psi 1 will be 0, psi 3 psi 2 will be 0, psi 3 psi 3 will be 1. It's like I will multiply with I, j with j, k with k. What will you get there? 1 upon 2 square plus half square plus half square. So what are you getting? 1 by 2 plus 1 by 2, sorry, plus 1 by 4 plus 1 by 4. So I'm getting 1 by 2 plus 1 by 2, I'm getting 1. It is normalized. The initial wave function is normalized. It means you have to get rid of the denominator. Don't worry. Psi t is normalized. So denominator has lost its significance. Understood? Tell me if not. I hope this is fine. I told you this before.
Yes, sir.
You need to ensure that you understand the numericals first. Theory will come and go, and I'll keep on revising the theory during the numericals as much as possible. The chapter is very scoring. Shall we? Next. You can always ask me to repeat. So now, suppose they have given us, suppose we measure E2. Like you calculated energy eigenvalue E2, where En is energy eigenvalue. Energy eigenvalue. So they're asking you to find the collapse wave function. The collapse wave function. Okay. So let's calculate the collapse wave function, people. What is the formula of psi after? Denominator has lost its significance. So it is just the value of psi n, just the value of psi n into the scalar product of psi n with the initial wave function. Okay, this denominator I'm not writing. If you want, you can write psi n, but it has become 1. People already checked that. So this is already 1. Not psi n. You can always tell me if I write something wrong. Initial wave function. This is already 1. So it has lost its significance. Let's calculate the numerator. So psi n is psi 2. Psi 2, I told you it is a wave function corresponding to the eigenvalue. Into psi n into psi phi. Now, what is kept with the psi n, people? It is 1 upon root 2 psi 1 plus 1 upon 2 psi 2 plus 1 upon 2 psi 3 into, sorry. Psi n is just psi 2. Psi n is psi 2, psi n is psi 2. What is psi I? Psi I is 1 upon root 2 psi 1 plus 1 upon 2 psi 2 plus 1 upon 2 psi 3. But what will happen during the scalar product now? The scalar product, like I said,
Only half will remain.
that's it. It's scalar product, people. So psi 2 and psi 1 will become 0. Psi 2 will become 1. Psi 2 will be 0. Only half will remain. It means your answer is done, people. What is psi after? Psi after is psi 2 into half, or the collapse wave function is half of the wave function of corresponding to the second energy eigenvalue. I hope the numerator helps you to understand the concept better. All good people, take care. This is the collapse wave function.
हेलो सर
बोलो।
यस मतलब psi 2 गिवन होगा ना हमको ये फैक्ट मतलब कुछ दिया होगा कि
हाँ, like they have to give us that find the like suppose we have measured that this is the energy, because in order to understand psi after they have to give us that what is the energy calculated or
मतलब इसके
हाँ बोलो
मतलब इसके corresponding निकालने के लिए वो उसने बोला था मतलब क्वेश्चन
हाँ,
दिया होगा
they have to give us or they can also make it a bit more advanced. They can ask you, they can use some data, they can ask you find the energy first, and like I said, suppose you find out energy is, let's say, minus 1.81, I think, so whatever was that, and let's say that was in hydrogen atom, that becomes which second excited state, third level, so that you understand it's psi 3. That also can happen.
Okay.
So in the chat box, so then this says that the wave function is collapsed into psi 2. That's correct. So absolutely, it has to collapse itself into psi 2 now, because you measure energy E2. Because you measure energy E2, so E2 is corresponding to psi 2. However, after collapse, you cannot have complete psi 2. The amplitude will be reduced. Intensity will be reduced, or whatever. Okay. So how much times of psi 2 will be reduced? So that's what we calculated, half times. Okay. Good. So the wave function is collapsed into psi 2. So there were 3 possibilities, people. Basically, white light was supposed to meet up a violet light, a blue light, and let's say red light. But when you light in darkness, you don't see it. It's simple. In darkness, we don't see which kind of a light is traveling by. And if we are trying to measure, if we turn on the lights, it will collapse itself to only one color all the time. And this is the reason, people, that what we are seeing around us, all the colors are collapsed colors. Because it's simple. Right now, we are seeing blue color, black color. Technically, we don't know what should be the color of this. It could be something else. But all of these are nothing but collapsed wave functions, people. All of these around us. Okay. Initially, like let's say before its existence, it could be made up of any random colors. All the 3 had equal probability for its existence. But once you measure, people, to destroy the wave property, to reduce itself to a particle property, then you get only one wave function. So you reduce itself to half psi 2. You reduce itself to half psi 2. Clear? Okay. Sure. Next. You got this one. You got half psi 2 is the final answer. So you got this one value. You did not get this one value. Did not get this one value. Our final answer is only this much. It's like polarization also. You can say that these were the two unpolarized. Not at all. It's just a layman idea I'm giving you. It's not correct. I'm just telling you. You can imagine it this way. Like you had an unpolarized light, and after putting a filter, you get a polarized light. Right? So you can compare it that way. So you get only one vibration or one wave function, which is psi 2, something like that. Okay. Sure. Next. Any questions, anyone? Achha, by the way, never be under an assumption that so in exam they will give us that if we measure E2 and I directly write half psi 2. No, people, you cannot always do that. Can you tell me why? Pardon? Your voice is breaking a lot, plus there is noise. I couldn't
So
hear
can
you.
you please repeat the question?
So the question is, suppose in exam they have given you this wave function. Okay, they have given you this, and they have also mentioned that we measure energy eigenvalue E2. They are asking to find the collapsed wave function. Logically, we already know the answer. E2 means it has to be related to psi 2. Our answer was half psi 2, so I'm saying this is the answer. But is it always possible that answer will be half psi 2 if they give you E2? That's what I'm saying.
No.
The function normalized now.
That's it. If the function is not normalized, then it's not half psi 2, then you will have the denominator. In that case, it won't be half psi 2. So never be under an assumption that it will be half psi 2. It will be some multiple of psi 2. That's for sure. You can write n multiple of psi 2. Now that n will be half if it is normalized, because there is no denominator anyway. Since there is no denominator, whatever is the numerator, that's your answer. But if it is not normalized, then you will have something in the denominator. So it won't be half psi 2. It will be some other multiple of psi 2 in that case. Okay. So never be under an assumption of that part. Okay. Chalo, proceeding ahead. Next. So suppose you can also create a small condition here that if I give you a wave function, this is just a formula, you can write more. So this is a formula. So suppose if I give you a wave function, let's say psi initial, whatever. Let's say this is C1 psi 1 plus C2 psi 2 plus dot dot plus Cn psi n. Okay. So if I tell you if psi 1, psi 2, psi n that we have form orthonormal basis. Form orthonormal basis. Okay. Then what is the relationship between C1, C2, Cn people? What is the relationship between C1, C2, Cn? Pardon? No, not that. Achha, linearly independent case. Yes, absolutely. But the thing is, you cannot directly write it. You need to remember that the value of psi I is 1. Okay. Now, sorry, there are multiple conditions. If psi 1, psi 2, psi 3 form orthonormal basis, and if psi I is normalized. Sorry, I have to give you if psi I is normalized. So if psi I is normalized, okay, then we know that the value of psi I is 1 people. So you will multiply this with this, and the value of scalar product idea is also valid because they follow orthonormal basis people. Okay. So psi 1 will multiply, psi 2 will multiply, psi 3 will multiply. What will be left with
C1 square C2 square plus so on is 1.
That's right. C1 square plus C2 square plus Cn square, that will be 1. Okay. Take a note. Any questions? Anyone? Anyway.
Yes, sir.
Okay. And if it is not normalized, people, if it is, oh, wait, hang on, I'm thinking something. C2 square, C2 square, C2 square. Okay, that's fine. Nothing. Sorry, I wanted to say this, that there is a small problem in this formula, small problem. Many students by heart this formula, it's a very popular formula, by the way. The problem is, people, what if C that I give you, the coefficients, what if they are complex numbers? I've told you that they are scalars. Scalars can be complex numbers. I've told you that since beginning. What if they are complex number? Then you need to remember when you say that they are normalized, when you apply this condition, you're actually calculating a bra vector here. When you calculate bra vector, actually what happens to C1 people? You write psi1, all of them
C1
become star. This becomes C1 star conjugate. Okay, so this will be psi2 and C2 star. Okay, and similarly this will be psi-n and Cn star. So actually this is not an absolutely correct relationship, because when you take product, psi1 will become 1, psi2 will become 1, sin will become 1. But the relationship will be C1 star C1, C2 star C2, and Cn star Cn. That is one. Okay, so C1 star C1 plus C2 star C2 and plus Cn star Cn. That will be one actually. This is an even general relationship. And only if the values are real, all the coefficients are real, then you can say that it's C1 square, C2 square, Cn square. So this is when all are real. When all are real. And C1, C2, Cn are real. In that case, you can directly square them up. But otherwise, take care of this fact. ठीक है. So I'll give you a question here. You tell me the answer of it. Okay. So the question is, they have given you psi t, which is given by a psi1 plus half I psi2 minus 1 upon root 2 I psi3. Okay. As a first check, okay, so they have given us that psi t is normalized. They have given us that psi t is normalized, and they have given us psi1, psi2, psi3 form orthonormal basis. See, they have to always mention that, because who said that all of them are eigenvectors? No? Only if they are eigenvectors, they will always form orthonormal basis. If we don't know whether they are eigenvectors or not, we cannot say whether it forms orthonormal basis or not. Okay? So find the value of A. It's an NAT, suppose. The value of A is dash. Calculate.
Sir, is it 1 by 2 plus minus 1 by 2?
But don't write plus minus, write either of it. But answer is correct. And you cannot write 1 by 2. You have to use, please remember people, a numerical answer type. You can use 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, dot, minus. Only these are the things to be used in NAT. You cannot use a slash, you cannot use plus, you cannot use star, you cannot use any of it. You cannot use race, you cannot use anything. You have to use only 12 of these individual values, whatever we want to call it. Okay? So in that case, you have to write 0.5. But answer is correct. And in this, 90 to 95% students face problem. They will get a very absurd kind of a value, because they have learned, most of them have learned that C1 square plus C2 square plus Cn square is 1. And in their head, it's always that these are constants, they are real. First of all, they worry about this thing I in it. Okay, and they will mostly do something like a square plus half square plus 1 upon root 2 square equals 1. They will end up doing something like this, and they'll get a negative value. Or they will do something like a square plus half I, like half I square plus 1 upon root 2 I square equals 1. They will end up doing this. Even this is wrong, even that is wrong. Both, and what I know, because I'm going to set a paper suppose. I know that some of the students are going to make this mistake. So whatever answer I'm going to get here, I will write it in the option. Whatever answer I'll get here, I will write it in the option. I know these are the two common mistakes. Some students will just equate the coefficients. Some will write I as if it's a coefficient in itself. And both of it will give you the wrong result, and I'll keep them in the option. Okay. But the true value is like, it has to be conjugated to the multiple. Let's calculate quickly. So a star into a plus half I star into half I plus minus 1 upon root 2 I star into minus 1 upon root 2 I. This is 1. So a star into a plus half into half is, okay, so half I star, so that's minus half I first of all, into half I plus minus 1 upon root 2 I star, so that's 1 upon root 2 I first of all, okay, because I becomes minus I now, so minus becomes plus. Okay, so 1 upon root 2 I into minus 1 upon root 2 I, this is 1. So a star into a, okay, minus I into I is I square, root 2 is 4, minus I into I is I square, root 2 is 2, this is 1. So a star into a minus I square, okay, so that's I square is minus 1 now, so this is plus 1 by 4, I square is minus 1, so this is plus half, this is 1. So what do we have? A star into a plus, sorry, plus 1 by 4 plus 1 by 2, so that's 3 by 4. This is 1. So a star into a is 1 minus 3 by 4. So this is 1 by 2. Sorry, plus this is 1 by 2. A star into a is like mod a square. Okay. So mod a is half. Mod a is half. And you can also say that a star into a is 1 by 4. And you can write 1 by 4 since it's a real value. It's a real value. You can say this is half into half. Whatever. But I think you can just write a star into a is mod a square, which is 1 by 4. So mod a is nothing but half people. Clear? Any questions? Anyone? Anywhere? Please ask. Shall we?
Yes, sir.
Proceeding ahead. Now, please give any probabilistic outcomes. I hope you are enjoying this. It's numericals, these are fun to be honest. Once you get the hang of it, now how you're supposed to do this, the numericals are very fun. Probabilistic outcomes. Okay. So suppose they ask you, like initially you have a wave function, like I gave psi I is a wave function of linear combination of psi 1, psi 2, psi 3. You want to find the probability that I will get psi 2 as a collapse wave function, or probability that I will get psi n as a collapse wave function. How do you do that? Okay. So probability that you have energy eigenvalue n, or you can say probability that you'll end up landing with the eigenfunction psi n t. Okay, it is simply given by the value of psi n into psi I upon psi n psi. I need to confirm this part, and here mod square. Now it's fine. Okay. Yes. This is probability of En or psi. Make a note of this. And also, people denominator will become 1 if psi n is normalized. I have written psi n once again. You can always tell this is incorrect. I have a habit to write psi n a lot. I have write psi I initial wave function. Now it's fine. So denominator will be 1 if at all it is normalized. So you can have only numerator in that case. Okay? You can also say so probability that you will end up getting energy value En corresponding to eigen function psi n. Probability of getting this, it will be just, you can say, the value of psi n into psi I square. And denominator becomes multiple in that case. It means this is when psi I is normalized. When psi I is normalized. Clear, everyone?
Yes, sir.
So in the previous question, tell me the probability. I can ask suppose what is the probability of getting outcome? Suppose in first case E1, in second case E2, and in third case E3. Each of them. Basically, I want you to find all the respective probabilities. What is the probability that we would have got E1? What is the probability that we would have got E2? What is the probability that we would have got E3? Calculate. What was the question, by the way? Question was psi I was given to you 1 upon 2 psi 1 plus 1 by 2 psi 2 plus 1 by 2 psi 3.
So you're missing I.
No, in previous as it, no, not previous as it, the previous of previous. Okay, leave the previous in this. Let me make it new question. Okay, so that's it. This is given previous of previous. The collapse wave function. So what is the probability of getting the outcome? Getting outcome even. Shall we? Shall. So what is the formula of probability of En? It is psi n, psi I, the whole square. Upon denominator, we have psi I. But you already know, if you remember, this is normalized. No? We calculated. So you don't have to write the denominator. This is already 1. So this is just the value of psi n, psi I square. So first probability, let's calculate. Probability that I will get E1. What will be that? That will be psi 1. And what is psi I, people? 1 upon 2 psi 1, 1 upon 2 psi 2, 1 upon 2 psi 3. 1 upon 2 psi 1 plus 1 upon 2 psi 2 plus 1 upon 2 psi 3. And now, so what do we have? Probability of E1. This will be psi 1 will be 1, psi 2 will be 0, psi 1 will be 0. I'm left with 1 upon 2. There is a square also, don't forget. So probability is half. And I think you're smart enough to tell me the next two answers directly without solving them. What is the answer?
1 by 4 and
1 by 4 and 1 by 4. Basically, it's the square of the individual coefficients, people. That's what you get because you got psi 1 into 1 by 2. Next time you'll have psi 2 into this. Next time you'll have psi 3 into this. But and then you'll have square. That's it. It's just the coefficient square, people.
Sir, wave function always make orthogonal basis.
Wave function is in the wave function is made up of linear combination of psi 1, psi 2, psi 3. They have to give us an example that they are orthogonal basis. If they mention that these are eigenvectors, then also they are orthogonal basis. Eigenvectors by default are orthogonal basis. But it's important for them. If they don't mention either of them, then I think 2 marks should be allotted to everybody. But in that case, maybe you assume that they are orthogonal basis. But we will still debate that they are supposed to mention that they are orthogonal basis, or they have to mention that these are eigenvectors corresponding to eigenvectors. Because if you remember, we did take a question in the class last time or maybe before, where I did not give you orthogonal basis, where I gave you psi 1, psi 3 had some value. Maybe I'm not sure, or we can have a similar question ahead. But okay, no problem. Okay, people. If they're not orthogonal basis, in that case, they have to give you the value. What is the scalar product value of this? In that case, they have to give you all the individual values of all the scalar products. If they are not orthogonal basis, because otherwise, if they are orthogonal, then this is 0. You don't have to worry about it. But if they are not orthogonal, then we have to give you all the individual values, like value of psi 1, psi 1, psi 1, psi 2, psi 1, psi 3. Right now, I'll need all the 3. Clear? So please also write. So similarly, our favorite word. Similarly, probability of E2 will be what, people? I can directly say psi 2 into this. Okay, psi 2 into this. Psi 2 into psi 1 will be 0. Psi 2 into psi 2 will be 1. Psi 2 into psi 3 will be 0. I'll be left with half, but then there is square. So you'll have 1 by 4. And probability of E3 is 1 by 4. Just one thing at the very end. People, sum of all the probabilities should be 1 at the very end. So see if you're getting 1 or not. Just verify whether your answer is correct or not. So that this will also help you trust in the formula more. So just calculate probability of E1 plus probability of E2. There are 3 eigenfunctions. So sum of all of them should be 1. See, LHS. So that's 1 by 2 plus 1 by 4 plus 1 by 4. So you're getting 1 by 2 plus 1 by 2. You're getting 1. Clear?
Yes, Guruji.
Nice. Okay.
Yes, sir.
Good. And okay, hang on. So we can basically create a general formula here also then. So if the psi n is given by C1 psi 1 plus C2 psi 2 plus keep on going plus Cn psi n. Okay. I can simply say probability that I will get value E1 is C1 square. Probability that I will get E2 is equal to C2 square. And probability that I will get En is Cn square. However, 2 important things. Thing number 1. How can I write this if C1, C2 are complex?
C1 star C.
So in that case, please take care of it. If they are complex, don't square them. C1 star C1, you will have to write C2 star C2 and your Cn star Cn if they are complex. Second, is this always valid or conditionally?
Condition, normalized.
Normalized. Psi n.
Normalized.
Don't write science, make it psi I. I have a habit to write psi, I told you that. Psi I. Condition is psi I is normalized. If it is not normalized, then also we can create a general formula. In that case, denominator is not 1. No? So people, can you tell me, suppose here, look at the formula. If suppose this, we already took a numerical that this was 1. If denominator is not 1, so if you calculate the denominator, what you will have? Like what will you get in the denominator every time you calculate En? Have a look at psi I. Or wait, I will give you. First, copy this. Chalo, let's not rush. Copy this.
Yes, sir.
Okay. So if suppose I give you that psi I is, like I said, C1 psi 1 plus C2 psi 2 plus Cn psi n. So we can create a general formula of probability of En. So it is not normalized, but orthonormal basis, that is still important. Only orthonormal basis only orthonormal basis. Okay. So like psi1, psi2, psi n, they are orthonormal basis, but psi I is not normalized. Okay. So in that case, probability of En formula will be, that is like we just wrote psi n, psi I mod square upon psi n, psi n. It's simple. Psi n, psi mod square numerator you already know. What is numerator for En? What will you answer for numerator only? Cn square. Huh? The numerator is just Cn square. We solve this already. Okay. So that was our answer earlier. Earlier our answer probability was just Cn square as we wrote here. Okay. But now denominator exists. And again I've done a small mistake.
Sir, I.
Yes, please. Okay. So if you calculate psi I, what you will get? Again, dot product of this with itself. Psi1, psi1 will be 1, psi2, psi2 will be 1, psi1 will be 1. In the denominator, you will have C1 square plus C2 square plus Cn square p2. Obviously, because denominator is not 1. Denominator is not 1. That's it. So this is a general formula for probability of En. That's it. Okay. Do one thing, because we're going until n here. Don't write n, just write plus. That's better. Don't give it an n limit, otherwise n will be confusion. That's it. And keep on going. So this is probability of En. In that case, we have a general formula. Otherwise, denominator will be 1.
Sir, if real, na?
If real, obviously, then otherwise if it's not real, then we have to write this as Cn star Cn upon C1 star C1 plus C2 star C2, and it goes on the dot. Absolutely. So that's always there. So this is the most general form, like most general. It cannot get any general than this. Okay. We are considering complex. We're considering it is not normalized. Okay. This becomes the most general. Actually, still it is not the most general. It is basically when we have orthonormal basis. It becomes more complicated if it's not orthonormal. Because in that case, when you take the dot product in the denominator, we are right now just multiplying psi1, psi1, psi2, and psi2, psi2. Otherwise, all the terms will multiply with each other. That will become a hell of a question. Okay. But you don't have to know that, so relax. But still, this is the general formula is this. Most general actually becomes this, and hence we have a formula. This is actually the most general. This is not most general. Absolutely. Okay. Next. We're still not done. I'm going to complete this whole topic. Okay. The last thing for the day and for this lecture, average value. Okay. So suppose they have given that you have a function is made up of psi1, psi2, psi3. But now we want to calculate what is the average value of the energy. Like for example, you know that water has different refractive index in response to different colors. I already told you that. What you have learned is the average value of that water. How have you calculated the average refractive index? When you write 1.33, it's average refractive index. So refractive index corresponding to the yellow color. Okay. Otherwise, it has different refractive index in response to red, violet, blue, green. It's different. Okay. So average value of anything, let's say of energy, suppose energy. So it is calculated as P1 E1 plus P2 E2 plus Pn En. Probability that you will get the value of E1 into the value of energy E1. Probability that you will get E2 into the average value of E2 plus probability that you will get En into the average value of En. That's it. That's it. So this many students directly by heart this as C1 square E1 and you know in the cycle like this.
Normalization, not complex.
Yes, normalization and not complex. Everything is heavily in your head. I'm so happy. Okay. So this we can write only when normalization is happening and the things are not complex. Yeah. Because you're not considering the denominator and you're also not writing C1 star, C2 star, everything respectively. So we will write the general formula here. We'll write the general formula. So for us, the value of E will be we can write C1 star C1 E1 plus C2 star C2 E2 plus Cn star Cn En the whole upon C1 star C1 plus C2 star C2 plus Cn star Cn. This becomes our formula. But yes, otherwise, if wave function is normalized and constants are real, which mostly you may have this, which if wave function is normalized, in that case, denominator loses its significance. So we just have numerator. Okay, we just have numerator. And if obviously all the constants are also just real, then it's C1 square, C2 square, Cn square respectively, right? Done, people. Write it. Write this value also. Okay. C1 like this energy item value. This is a more popular formula. C1 square E1 plus C2 square E2 plus Cn square N. And you have already understood the two important conditions where you can use this. Real and normalized. Constants must be real and wave function must be normalized. So in that question that we took, suppose if I give it, first of all, just tell me the 100% correct value, not 100% correct, of the electron volt in hydrogen atom. This is minus 13.6. This is minus 3.51, right? And 1.85. I'm also asking you. I'm not sure. So correct.
So 4 divide कर दीजिए ना हो जाएगा.
We can do that any day, but still. So okay. So let's take this one. Suppose it's given to you, or basically they won't give you this. They will give you that it's a hydrogen atom. So that question only people that you know I have given psi I was 1/2 psi1 plus 1/2 psi2 plus 1/2 psi3. People, what is the average value of the hydrogen atom? Average energy. Average energy of hydrogen atom. And also, I just wanted to thank Sanju, Akash, Shruti Sri, Kanaya, Arun, Abhay, Rishita, and Sunita. I have received all of your testimony. Beautifully, you have written everything. It was very heartwarming. I felt really good on 31st, and some of you also sent it on first yesterday also. So both the days. Thank you for that.
Thank you to Sir Noctism.
Because you have put your efforts in writing that, I have seen that clearly. So. Anyone with answer? So what is it? It is normalized. We already know. The constants are also real. So I can directly write half square into minus 13.6 plus not half square, 1/2 square into
So 1 by
13.6.
2. Yeah.
So that will be 1 by 2 basically. Then 1 by 2 square into minus 3.51, and then 1 by 2 square into minus 1.85, and then whatever is the answer. Got anything? Just verify among yourselves. Okay, so whatever is the answer in electron volts. Okay, we'll stop here. We'll meet in the evening. We'll continue with this chapter, and we'll be completing this chapter also probably today, and then we'll have the application also in the future. Let's see. Thank you so much, people. You are the lead.
Thank you.
you so much.
Thank you, sir.
No
Thank you, sir.
Thank you.
हेलो सर
But it was not in effort. It was continuous.
थोड़ा मदद चाहिए
Sure. What continuous? I did not understand. Pardon?
सर मतलब थोड़ा
No,
गाइडेंस
no,
चाहिए
not you, Aditya. Sorry.
Sir, I told that was not in effort. That was continuous.
Acha, okay. But still, whatever it is. Thank you. Okay, हाँ, Aditya.
हाँ सर क्या है ना मेरा सेमेस्टर 5th सेमेस्टर 27 जनवरी को है
हम्म,
मतलब
okay.
3 फरवरी तक
Right. 27 and 3. Okay. Fifth semester. Okay.
हाँ उसके बाद अगर प्रैक्टिकल बोलो मतलब टाइम टेबल अभी तक प्रैक्टिकल का नहीं निकलेगा अगर निकलेगा तो उसके बाद एक वीक भी चला लेगा मतलब अगर 10 फरवरी तक
Right. Okay.
हाँ तो थोड़ा क्या कम समझ में नहीं आ रहा
मुझे बताओ तुम्हारा फोर्थ सेमेस्टर में परसेंटेज कितना है बीएससी में?
सर तो मतलब नहीं निकला है अभी रिसेंटली हुआ ना कोरोना की वजह से अभी अक्टूबर में दिया है इसलिए
बट रफली
रफली 80 मिनिमम
तो listen, अरे 80 वाला तो relax कर. As far as you are just passing out your BSc, don't take it too low right now. Anything about 8, if your score is already very good, so this time if your BSc score goes थोड़ा सा down also, it's fine. You can focus on JAM easily. But yes, ensure that you don't lose your marks too much in your BSc exams. Exams are you have to give your exam. You cannot skip your exams. So you give the exams obviously, but don't take that much of load right now for your college exams. You could have taken if your percentage was already above 80, then it's fine. You can relax.
ओके सर थैंक यू सर
No problem.